Hi, and welcome to lecture number 2 of Advanced Power Plant Design in the spring 2014 semester. Once again, I'm Nick Siefert, and this is the videotaping of the lecture number 2. This is a review of undergraduate thermodynamics as applied to power plant systems. So we're going to be starting off with a vocabulary review of undergrad thermo, so that we're all on the same page here and speaking the same language. So let's start with some definitions. I want to point out the difference first. I want to point out the difference between local and global equilibrium. Right. So in this course, we're going to be assuming that there's such thing as local equilibrium. And when you're able to define a local equilibrium, you can actually calculate such things as a local pressure, a local temperature, or a local chemical potential and chemical composition. So what equilibrium here means is that the rate of all forward reactions is equal to the rate of backwards reactions. So that's what it means to be in equilibrium, is that for every single possible type of reaction, such as a combustion reaction or any other type of reaction, if something's really in equilibrium, then the rate of all forward reactions is equal to backwards reactions. And what we're assuming is in some really small cube of space, maybe 1 micron by 1 micron by 1 micron, there's still a lot of particles in there. And in that small 1 micron by micron, it's where we can define that there is one temperature in that region, one pressure, one chemical potential. So that's what we mean by local equilibrium. But globally, the system is far from equilibrium. Inside any control volume, there's not going to be necessarily always constant pressure or temperature or chemical potential. Right? There's going to be spatial gradients in these potentials throughout the system. And that means overall, inside of a control volume, we have a non-equilibrium situation in which the rate of either forward or backwards reactions is greater than the opposite reaction. So inside of a control volume on net, if your control volume is a combustor, a net, there's going to be forward reactions towards carbon dioxide and water vapor and away from methane and oxygen. Okay. I do want to point out in this course we're always going to be assuming steady state. This is not going to be a course that looks at dynamics, right? And by steady state, what I mean is that the variables such as the pressure and temperature are not changing with time. So steady state does not mean global equilibrium, right? What it just means is that the variables aren't changing with time. We're not going to study the dynamics of compressors or turbines, like how you ramp up or how you follow a peak load or anything like that. That's not the intent of this course. So in our cases, we're going to be assuming steady state, in which inputs into a control volume are constant and the outputs are also constant with time. It means the control volume itself is not changing with time either. Okay, another definition I want to point out before we get too far is a state function. I want to point out a state function is a property of a system that depends only on the current state of the system and not on the way in which the system acquired the state. So a state function describes the equilibrium state of a system. So if we're talking about some 1 micron by 1 micron by 1 micron region, we can define a pressure and a temperature, an internal energy. These are all state functions. They only depend on the current state of the system, whereas we can't really, because such things as the work or heat out of a control volume are functions of the path taken by a system, work and heat are not state functions. Okay, I want to point out that there's a lot of different types of thermodynamic variables. some of which I'll be calling equilibrium thermodynamics, some of which I'll be calling kinetic variables. So I just want to give you a feel for some of these variables. We'll define a lot of them throughout this entire lecture. So there's, in thermodynamics, you're going to be seeing a number of geometric variables such as volume, lengths, areas. You'll be seeing thermodynamic variables, which are state functions, like pressure, temperature, chemical composition, the entropy inside of a control volume, the internal energy inside a control volume, the enthalpy within a control volume, the Gibbs free energy within a control volume, or the Helmholtz free energy within a control volume. Note, for most variables that are uppercased in this course, it means that they are speaking of, let's say, like big S means that the sum of all the entropy inside of a control volume. I do want to point out that temperature is a one exception to this rule. I mean, temperature, we can talk about a local temperature, and doesn't necessarily mean the temperature for the entire control volume. Okay, so then we've got kinetic variables, and we have kinetic variables of a material, and then we have kind of overall flux terms. And these variables, in order to have any type of flux, you have to have some kind of global non-equilibrium situation, in which case you need to know something about the kinetic variables of the material. Kinetic variables of a material are items such as its diffusivity. Mu here in this case is its viscosity, sigma is its electrical conductivity, and kth here means its thermal conductivity. These are properties of a material that tell you how much flux you get for a certain amount of driving force. Right? So the fluxes are things like velocity, current density, the heat flux, or the mass flux, gamma in that case. Okay, then there's also system variables. And by system variables, I mean these are variables that are of a control volume. So Q dot would be the rate of heat leaving a control volume. Here we're going to define Q dot being positive if it's the rate of heat entering a control volume. W dot being positive is the work leaving a control volume, and sigma dot IRR is the irreversible generation of entropy within a control volume. These are variables that are speaking of an entire control volume. Okay, we also have extrinsic variables. These are ones where, like U, H, G, and F, the capital ones, and big S. If you were to double the number of if you were to double the volume and double the number of the moles, then big U, big H, big G, big F, and big S all would double. Intrinsic variables are the ones where if you change the size and the number of atoms, so the volume and the number of moles, these ones don't change. And these are things such as the pressure, temperature, and the density, as well as little hat U, little hat H, little hat G, and little hat F. Where the little hat, the lowercase with the hat over it, means like little hat U would be the internal energy per mole. Little hat H being the molar enthalpy, and little hat G being the molar Gibbs free energy. Okay, so now let's talk about some of the laws of thermodynamics. We've got 4 different laws, 2 of which we're going to focus on mostly in this course. So the 0th law of thermodynamics says that if system A, control volume A, is in equilibrium with control volume B, and control volume B is in equilibrium with control volume C, then A is in equilibrium with C. It's just a basic definition from logic. The second thermodynamics, which is a really, really interesting one, says that the modern our statement of the modern statement of the first law of thermodynamics says that energy is conserved in any process involving a system and its surrounding. which is equivalent to saying the total energy of the universe is conserved and a constant throughout time. So energy can change from one form to another. It can go from gravitational into thermodynamic into heat. Right? And if it was just the first law, there would be no reason why you couldn't turn heat back into energy, into gravitational potential energy. But we'll find out. The second law is a law that gives directionality. It tells you there's a directionality to which energy gets transformed. So the second law can be stated as there exists no thermodynamic transformation whose sole effect is to extract heat from a reservoir and to convert that heat entirely into work. Okay. So you cannot turn heat 100% into work, is what the second law of thermodynamics says. But you can turn work into heat. So it's saying that there's a directionality to it. And actually what the second law was in this last century has been turned into, the equivalent form is to say the entropy of the universe is non-decreasing. So that means the entropy of any isolated adiabatic isolated control volume will either will increase, or eventually when it hits equilibrium, it will the entropy will stay constant from there on out. So the entropy will increase until it reaches equilibrium and then just flatlines. So because once you hit equilibrium, you're at the state of highest entropy. Okay, and I want to point out there is a third law of thermodynamics which is used to define the zero state, or the entropy at zero temperature. So here we're defining, it's basically a statement of, so that we can define entropy, what we're doing is we're stating as the temperature goes to zero, then the entropy is defined as going to zero too. In this course, as I said, we'll focus mostly on the first and second laws. So let me kind of state them over again. The first law is saying the total energy of the universe is a constant. So if we were to sum up all the energy states of all the particles in a system, then that number would stay constant. And in kind of an analogy of thinking about it, it would be if somehow the amount of money were fixed in the universe, right? If it could be in different forms of denomination, but if somehow we fix the number of total amount of money to be a constant, that would be something like what the first law is. Some kind of total number is a constant. The second law says that macro states evolve into new macro states in which the total entropy is the same or greater. The trend is towards systems with a greater and greater number of particles, because the more particles you have, the more microstates in any macro state. The entropy typically is increasing with the number of particles. So this would be like saying, so when you combine the first and second law, and this is the analogy that I'm going to use here, let's say the amount of currency was fixed such that you were forced to only have $100,000. You could never have more. You could never have more than $100,000 in money anywhere in the universe at any point in time. But if there was also a law that the number of coins could only increase or stay constant in time, right? If the number of coins could only increase or stay constant with time, what we would find is that slowly over time, what it means is you would have to be able to turn, let's say, quarters into nickels, right? If there was some law that said that you could exchange 5 nickels for 1 quarter, but you couldn't do the opposite, what would happen would be over time, you'd see a trend to more and more coins. So that's kind of what I like using here as an analogy, is that the first law is kind of a statement of there's a constant amount of energy. But the second law is saying that the currency denomination in which that energy is in degrades over time, so that things may have started out as dollar bills and then slowly over time get converted into quarters, get converted into dimes, into nickels, and into pennies. And that's what we're seeing what happens. And so here in this analogy that I'm using, temperature is like the average type of coin in any, when you look locally, right? It's the type of coin being used. So if you had a bunch of dollar bills lying around, it's like you're in a region that's very, very hot. There's a lot of energy per coin, right? But when you're in a region where there's a lot of pennies, it's the equivalent of being very, very cold. There's a lot. There's very little money per coin, whereas when you have dollar bills lying around, it'd be a very high. In this analogy here, like if you had a dollar coin compared to a penny, the dollar coin represents energy such as like a very high energy photon, and the pennies here maybe represent very low energy photons. And the trend is for so let's say dollar coins to be slowly converted into lower forms of currency. So that's what the second law is stating, is that the number of coins cannot decrease with time in this analogy. Okay, so let's go through a little bit more of a review of thermodynamics, just so we're clear on all the terms. What I'm going to be talking about next is the review of the potentials. And these are potentials such that when there are gradients in these potentials, there's going to be flux of something. So let's talk about that a little bit. So one of the potentials is pressure. And the pressure, as we'll find with these potentials, they're all ratios. And they're all ratios in which the numerator is some kind of energy term, and then there's going to be a denominator. So pressure is the ratio of kinetic energy per volume, which is exactly the same as force per unit area, right, due to the thermal collisions. Right? You can show that force per area due to thermal collisions is exactly the same as the kinetic energy per volume. So it has units of joules per meter cubed, or newtons per meter squared, which is also pascals. Okay, the next term, potential, is chemical potential. Chemical potential is when you sum up all the non-electrical, so non-electrical means if you were to get rid of any electrical field, but you were to add up all the free energy, all the energy sources that aren't associated with electric fields, and then you were to divide that by the total moles of species, or you could take a derivative of the energy per mole of species. So the slope of the free energy with respect to a change in the number of moles of species. And so the chemical potential includes all the kinetic energy, the rotational energy, the vibrational energy, and the chemical energy. And it's got units of joules per mole. Okay, so that was the second. The third thermodynamic potential is temperature. And once again, we're seeing it's going to be a ratio, here, a derivative of energy with respect, so the derivative of total energy with respect to total entropy. And so here the units are joules divided by joules per Kelvin. And what you're left with is just Kelvin. So it's kind of, it looks like it's a little bit different from the other potentials, but it really is an energy divided by something. It's just that something happens units of joules per Kelvin. And so this is one of our potentials. So here, entropy is defined as the logarithm of the number of indistinguishable microstates associated with any given associated with the given macrostate of the system. Right. So it measures the energy divided by the number of equivalent ways the system could look the same. And this is kind of like in that analogy I mentioned in the last case when we were talking about money and coins. Temperature had something to do with the type of denomination of the coin, the average denomination of coin in any region. So if you had a region with a bunch of pennies, we would say it's cold, and if we were in a region where there was a bunch of dollar bills, we would say it's hot, right? Temperature is not about the total energy in any region, it's about the type of denomination of the coin. So we say we say that the energy from the sun is hot compared to the energy from the earth, right? Not because of any, well, in this case, if we were to sum up all of the sun, right, there's going to be more energy than what's coming from the earth. But what we mean by temperature is it's the quality of the coin, or really how much energy there is per entropy. And as I said before, entropy is largely a factor of how many different molecules there are. So in some ways, we can think of it as a total energy per molecule, right? But that of course, is the chemical potential. So entropy is a little bit different than number of molecules, so the analogy is not obviously exactly the same. And I want to point out there's a couple other potentials when you do have electric fields. In that case, such if you're looking at batteries or fuel cells, you're going to have something called the electrical potential, which is the total electrical potential energy per charge, and that's going to have units of joules per coulomb or volts. Right, and the way to think about it, it's the amount of work required to move a proton from potential is equal to 0 to the actual potential of that location, location XYZ. So you could sum the electrical potential and the chemical potential if you put the two terms in the same units. So if you notice right now, electrical potential was in joules per coulomb, and the chemical potential was in joules per mole. But if you knew the charge per mole, so if you had some kind of ionic species like a proton, maybe a proton in an aqueous solution inside of maybe a PEM fuel cell, you could define the chemical potential of protons, in which you could define an electrochemical potential, which is the chemical potential plus Z times F times the electrical potential, where Z is the charge on the species, and F is Faraday's constant. So I just want to point out that there are a number of different thermodynamic potentials. We'll focus in this class on the top three. In the other courses I've taught, like in fuel cell systems, we look at these other two on the bottom. Okay, so just as a reminder, that there were conjugates, and this conjugate here meaning what you have to multiply by the potential to yield units of energy. So this is just a kind of reminder that in all cases the potential, when you multiply, in this case, if you multiply pressure by volume, or you integrate pressure times dV, you get units of energy. Right? So particle number or the chemical potential time the integral of the chemical potential times the change in the number of particles. Once again, that yields units of energy. Entropy is conjugate to temperature, and charge is conjugate to voltage. So here I want to use a example. It's a photon example to kind of understand entropy, and once again, this is I'm going to be referring back to that analogy I had with coins. So if we just had the here, let me first discuss what we have, what I'm showing here up on the screen. We've got different energy levels, and these are the vibrational energies of of a photon. So if it's an n equals 4 state, it's a highly energetic photon. If it's n is equal to 0, there's virtually no energy in the photon. And so what I'm showing here is that we have, let's say, a UV from the sun, UV photon from the sun, and it's in a state n is equal to 4. And on the right, we have some IR photons leaving the Earth, one of which is in state 2 and 2 of which are in state 1. So if we sum up the total energy, what we find is the total energy is equal to 4 in both cases. So there is no violation of the first law of thermodynamics. Energy is conserved as we go from one process to the other. But what we'll find is, according to the second law of thermodynamics, only one route from left to right is allowed. We're not allowed to go from right to left. So the reason here is that there are more available options when you have more particles. And there's actually more microstates associated with the case on the right than there is on the case on the left. The case on the left, there's only one way, there's only one particle, so there's only one way to draw it. So the number of microstates is 1. So the entropy is equal to Boltzmann's constant times the logarithm of the number of microstates. So in this case, the logarithm of 1 is equal to 0, and the logarithm of 1 is equal to 0, so the entropy on the left case is 0. So if we were to calculate the temperature, in this case, we would have 4, so we'd do the energy 4 divided by 0, and we'd get infinity. So this is saying is the case on the left is near infinite temperature. On this case on the right, what we have is we have energy is equal to 4, but there are multiple different ways in which we could potentially draw this diagram. If we could somehow distinguish between some of these particles, if we could distinguish between the ones in the n is equal to 1 state compared to the n is equal to 2 state, then we could swap them, and what we'd find is that there's different ways in which this configuration would be allowed. And in that case, what we would find is that the entropy is going to be a logarithm. Here it could be like the logarithm of there could be at least two different ways of drawing that, if we could distinguish from the n is equal to 2 state from the n equal to 1 state. And the n of logarithm 2, of course, is greater than 0. So what we find is that the entropy increases as we go from the left to the right. So that means we cannot go back from the right to the left. And this particularly becomes the case when we have a large number of species, in which we can start getting to logarithms of 10 to the 23, right? It doesn't take much for the entropy to increase. So this is an analogy of what the second law is saying, is that there's a directionality that this entropy has to be increasing. Okay, so now we're going to start looking at how do we actually put this into practical use, and we're going to start looking at the equations we'll use throughout this course. We're going to do that by defining system boundaries, and we're going to be defining the variables that we're going to be using in the first and second laws. So let's start with the first law. So the internal energy of a control volume is big U, and it's all the stored chemical, vibrational, rotational, and kinetic energy inside of the control volume. So the fact that the molecule is moving around, it's rotating, it's vibrating, and it also has the potential it may have chemical energy, such as its potential either to be combusted, or maybe its potential energy to be condensed into the liquid state. So these are all what we mean by the chemical energy. Okay. The next one we'll be looking at is big Q, and that's the heat. And heat is defined as a very strict definition. It's the thermal energy transferred across a boundary. And there's always a certain temperature associated with heat, right? Because you need to know the temperature at which it crossed the boundary. Because there may be different temperatures across the like any given control volume may have the temperature at the boundary may be changing across the boundary. Or you can think there may be a region in which hot thermal energy is entering and cold thermal energy is leaving. So remember, for each heat source or sink, or every source of thermal energy transferred across a boundary, there's going to be a certain temperature associated with it. And here in this course, we're going to be defining Q as positive if it's heat added to a system. Right. And when we're thinking about what I mean by heat is transport of energy that has entropy. So in addition, when you're transporting heat, not only are you transporting energy, you're also transporting entropy. So, and what I mean by transferring entropy is that when we mean let's say we're sending in heat into a system, let's say if this is some heat exchanger, what's happening is phonons are actually crossing through, if this is a metal heat exchanger, phonons are vibrations of lattices inside of a solid, very much like photons being vibrations in the electromagnetic spectrum. And so these phonons are crossing the boundary, and these phonons, because they're randomly distributed, they can actually carry a lot of entropy as well as carrying energy. So the way of thinking about it is that this heat transport is like coins crossing over a boundary, and in the case of heat, it's fairly low denomination coins. For work, what we're talking about is if in this analogy, work is the transport of energy with no entropy. It's like if you could transfer money across a boundary all at once in one denomination bill. That's kind of the way I think about work. Work is a transport of energy that has no entropy. It's like a wire transfer, right? It happens instantaneously. You don't need to carry it's not like carrying pennies and giving pennies to your friend, right? You know, giving pennies to your friend to pay them back is like giving them heat. Whereas if you did it one electrical a wire transfer, that's kind of like work, right? It's transport of energy with no entropy. And as we saw before, you can get no entropy with the whenever you have something like the logarithm of 1. Whenever it only takes one variable to describe the amount of energy in exact detail. So the analogy here is to know how much energy is in, like let's say if I lift a book up off the ground, and I want to know how much gravitational energy there is, I only need to know one thing about the book, as well as its mass. But once I know its mass, there's only one thing I need to know how much work there is, and that's its height. So there's only one detail, and that's height. So the logarithm of 1 is 0. So we say that the gravitational potential energy has no entropy. So if you could transfer that gravitational energy across a boundary, then we would say that work has transferred into or out of a system. And here we're defining work to be positive if it is work that is taken, if it leaves the system. And the reason we're defining it this way is that we have a power plant, and I want the answers to come out positive when we're building power plants. I don't want negative values when we're designing power plants. But heat here is heat positive if it's entering if it's coming into a system. Okay, so we're going to be needing a couple thermodynamic potentials in this course. I first talked about the internal energy. Right, the internal energy was all of the kinetic, rotational, vibrational, and chemical energy in the system. There's one main other one we're going to be using, and that's the enthalpy. That's H, and that is when you look at the energy in the system plus looking at the work needed to make room for it. So that's U plus PV is equal to enthalpy. So enthalpy is very, very close to the internal energy, except for it's got this PV term. And we're going to be using enthalpy a lot in this course. So it's very similar to the internal energy, except for this PV term. Then there's the Helmholtz energy, which we won't be using in this course, and that's if you take the internal energy minus Ts. So it's the energy needed to create this system minus the energy you get from the environment. And then the Gibbs free energy is U plus PV minus Ts, which is the total energy needed to create it and make room for it minus the energy that you'd be getting from the environment. So the ones to really focus on here are enthalpy, because that's the one we're going to be using the most in this course. These, I'm just putting up these. I just want to make sure that these were in words that I was talking about in the last slide. Okay, so we're going to start off with some control volumes, and we're going to be looking at what the first and second laws look like. First, for closed systems. So closed system is one in which there is no input or output of material of moles of actual like molecules or atoms entering or exiting the system. But the system may be in thermal contact with the environment in this system. So here what we'll see is the equation for the first law of thermodynamics is that the change in internal energy within a control volume is equal to the heat entering the system minus the work leaving the system. It's pretty straightforward. And so the entropy, the change in the entropy within the control volume with respect to time is equal to the entropy associated with thermal energy plus the irreversible production of entropy within the control volume. So let's think about it first in that money analogy. So from the first law, what we're saying here is, remember as we said, the total amount of money cannot change. So the amount of money in a control volume is going to be equal to the amount of money I add into the control volume as far as heat, and it's going to be decreased by the amount of money that I take out as far as work. Right? And remember, the only reason why one that shows up as positive and one is negative was just how I defined work and heat. So let's talk about this, the other one. The change in the number of coins, or the change in the number of entropy, the change in the number of coins in the system is going to be equal to the number of coins added that are added in heat plus the number of coins that are generated within the system irreversibly, is the way to think about it. So there are coins associated with heat, whereas there were no coins associated with work, right? Because it was all one, and it was all transferred in one coin here, in logarithm 1 being here 0. So the way to think about entropy is that we have coins entering because of heat, right? And we have the production of coins as quarters gets turned into nickels, or nickels start getting turned into pennies. So if you're adding in heat to the system and there is zero reversibility, then ds is going to be positive. Right? And the second law, the one thing about the second law is that it is sigma dot irreversible, which can only be positive or zero. ds by dt can be either positive or negative. Q dot over T can be positive or negative. But the second law of thermodynamics, what it's really stating is that sigma dot irreversible has to be positive or zero. Right? That's what I was saying before. The turning of nickel, you can only increase the number of coins. Right? At no point in time when you include both the coins inside and outside of the system can there ever be a decrease in the number of coins. If we have steady state, like we're going to be looking at in this class, then the du by dt and the ds by dt terms are going to drop to zero. Okay, so now let's get a little bit more complicated and let's talk about open systems. So for open systems, we're going to now include one more term in each of the equations. We're now going to not only going to have the heat and the work, we're going to also now include flow of material into and out of the system. So we now have these sigma terms, sigma, and then where it's sigma being the summation of the number of moles of species I times the enthalpy of species I, the molar enthalpy of species I. So that's one of the terms that shows up. And that's the one showing up in the first law of thermodynamics. So here, once again, we still have the du by dt and the q dot and the minus work. We're just adding one more term. And here I have that summation showing that n dot is positive if it is entering the control volume, and n dot is negative if it is leaving the system. So, but once again, the overall kind of in the analogy I've been using is that the total amount of money is constant. The number of coins is going to only increase. So that sigma dot irreversible is either positive or zero. But all the other terms in that equation, like ds by dt, s hat, or n dot times s hat, all these can be positive or negative. Q dot over T can be positive or negative depending on if it's entering or leaving the system. But what has to be true in order to not violate the second law of thermodynamics is that sigma dot irreversible is greater or equal to zero. So if we have steady state, we're going to have the du by dt once again, and ds by dt terms drop out. So what I do want to point out is what we have is a h hat and s hat, and we're going to have to figure out how to calculate h hat and s hat for species that are entering or exiting a system. So that's going to be what we're going to be looking at in the next couple slides. As we've seen before, the enthalpy was equal to the internal energy plus P times V. So when we take this on a molar basis, the molar enthalpy is going to be equal to the molar internal energy plus the pressure times the molar volume, the volume per mole. That's the equation. But oftentimes what we need to know is how does the enthalpy change? Because we may be able to look up in a textbook what the enthalpy is of a species at room temperature and pressure. But we want to know, well, how does it change when you change either the pressure or temperature? So the first thing I want to point out is if you have an ideal gas, then the enthalpy, or molar enthalpy, is not a function of pressure. It's only a function of temperature. And it's so the change from temperature 1 to temperature 2, right, so the enthalpy at temperature 2 minus enthalpy at temperature 1 is equal to the integral from T1 to T2 of the specific heat at constant pressure, C sub P, times dt. Now, C sub P may be a function of temperature, so this may not be the easiest integral. But as we'll be finding out in a few slides, C sub P can often be approximated as a constant plus another constant times temperature. So C sub P often looks like C sub P at 300 K plus beta times T. So when you put that into as C sub P into the equation, what you'll find, so if you use this linear ideal gas with a linear approximation of the specific heat, you find that the change in the from enthalpy from state 2 to state 1 looks like this equation here, which I'm not going to go through all the terms, but notice it looks like a C sub P, you know, with kind of this minus beta term, where beta is the how the specific heat changes with temperature. And if beta went to 0 in this equation, what you just have is C sub P at 300 Kelvin times the difference in the temperatures. And what I want to point out is if you have a mixture, a gas mixture, ideal gas mixture, let's say of nitrogen and oxygen, the enthalpy of the mixture, the enthalpy difference of the mixture, looks like the summation of the mole fraction of species I. So if it's 80% oxygen, or 80% nitrogen and 20% oxygen, then it would look like the summation of 80% times the enthalpy difference for the nitrogen component, and then plus 20% times the enthalpy difference of the oxygen component. And that's all on a per, then you have it as the per mole of the mixture, the enthalpy difference. Okay, next thing I want to point out is we're going to talk a little bit about the entropy of a substance. And the entropy of a substance increases with temperature. As we saw from that third law of thermodynamics, it goes to 0 when the temperature is 0. A perfect crystalline structure, there is only one way to describe it, is the way that I would put it. There's a limited amount of ways in which you could actually draw the structure. It's not vibrating and rotating or anything, it's just a perfect crystal. So in that sense, its entropy is 0 when it has stopped vibrating or moving or anything like that. So that's one way to think about why the entropy of a solid is 0, is that it doesn't take much information to describe the actual state of the system. Whereas when you get to the gas, like, you may need to know a lot about it, like which molecule is here, how fast it's going, also is it vibrating, is it rotating, those type of questions, right? There's a lot of information you need to know. And of course, so what we see, the entropy increases with temperature and there's jumps when you hit like melting points and boiling points. And these are the jumps that are occurring. And so the entropy of a gas is greater than a liquid, which is greater than a solid. But of course, you can still have gases turning into solids, solids turning into gases, all sorts of that, right? From the second law, what we said was, and this is, we look at the bottom, the irreversible entropy generation within a control volume has to be greater than or equal to 0. And what that means is when you rearrange that equation, the other way to putting that is that the sum of the three terms, these two n dot terms for all the mass that's moles that are entering or leaving, and as well as the entropy associated with heat, that term, when we're in this way, has to be greater than or equal to 0. And that's what that's what the second law of thermodynamics is stating. what I want to point out is that there's a difference between sigma dot and S hat, even though they both have the term entropy associated with it. They're very different things. And so one way of thinking about it is, let's say we draw a control volume and we have liquid water entering, and we have gaseous water or water vapor leaving the system. So that's going to be, we have a control volume, we have liquid water entering, water vapor leaving. So in this process, S hat of the material leaving is greater than S hat of the material entering. So in this case, but we also know that there needs to be heat added to the system, right? So the way to think about it is, it's like we're adding in a bunch of pennies in the form of heat, and we're getting a bunch of pennies out in the form of the gaseous water. And if in this analogy here we think of the water having a low entropy, and then the gaseous having a lot of entropy. So what I want to point out is that we could have a situation in which the irreversibility, the sigma of the irreversible, will equal to 0, and that would be exactly the case when the flow rate times the entropy difference of these little S hats were equal to Q dot over T, right? And of course you could solve that equation to figure out the temperature in which you would have no irreversible entropy generation if you were to boil water, right? And of course what you'd find is that temperature is, if the pressure is 1 atmosphere, then the temperature is 100 degrees C. So what this is saying, the second law is saying that if you had water and it were turning into gas, you can do that without generating any entropy if you did it exactly at 100 degrees C. So if the heat were came in at exactly 100 degrees C, you could do this without generating any entropy. Of course, it's really difficult to get energy into a system if there's no driving force for it to go into the system. So inevitably what you find is that in this case, Q dot is going to end up being, you typically need to use a higher temperature to actually drive heat into the system. And when you do that, you can see that this overall term is going to be slightly greater than 0, because the T, as you increase T, that term with the minus out front gets smaller, and you have now a term that's greater than 0. So it's saying you can boil water at 1 atmosphere if the temperature of the heat entering the system is greater than 100 degrees C, and the temperature itself is, let's say, at 100 C. You cannot do it if the heat is less than 100 degrees C, if the thermal energy is less than 100 degrees C, right? Because what you'd have is you'd have sigma dot irreversible being less than 0, and that violates the second law of thermodynamics. Okay, so I'll do this very quickly for some of these other systems. You could have calcium carbonate go into lime, calcium oxide, plus CO2. So once again, what we have here is the entropy exiting is greater than the entropy entering, because we have more gas species and the same number of solid species. So once again, we're going to have the case that there will be a temperature, and there will be a certain temperature at which we can remove CO2 from calcium carbonate and not generate any entropy. But it would take place really, really, really slowly, because there would be no driving force. So to have this take place in a reasonable amount of time, we're going to end up having to use heat of higher quality than what would be the minimum set by the second law. But you can't go lower than that minimum, or else you won't get the CO2 to come off. Okay. Now, in the third case, we have the case in which the entropy of the species leaving is actually less than the entropy of the species entering. So what does that mean? Right? So what that means is that we need to have heat leave the system, right, and carry some entropy out of the system in order for this to take place. So this could only take place if this were an exothermic reaction in which heat were leaving. Right, the first two I showed you actually turned out to be endothermic. They need heat. Right? This third one is exothermic and releases heat. And so in this case, what we would find out is that there's a certain temperature at which this reaction will occur and generate no irreversible entropy. But in this case, if we go above that temperature, it's not going to happen. So we actually need to stay below the temperature. And because we need to actually be below the temperature for any finite rate, for this to happen in a finite amount of time, we'll find we're going to be generating some entropy. As long as we are below the temperature at which they were, such that if you were to solve this equation, sigma dot would be equal to 0. Okay, and the last one I just want to point out is you can have some weird situations where it's not obviously intuitive if the entropy is greater for the species entering or exiting. And that's this is for the case of the water-gas shift reaction, where you're turning carbon monoxide into carbon dioxide, so that you can turn carbon monoxide, basically get the energy content out as hydrogen rather than carbon monoxide. And we'll talk about this in our class, because at coal gasifiers, we're going to be wanting to generate hydrogen, so we can use that hydrogen in turbines or in PEM fuel cell cars, right? We don't want carbon monoxide. We want to be able to generate hydrogen, use that, and then sequester the CO2. So this is actually an equation we'll use throughout this course. Just want to point out that it's not intuitive whether the entropy is greater or less. In that case, you definitely need to look up what that is in like a textbook. In the last slide, we were talking about the entropy change due to chemical reactions. In this set of slides, in this slide, we're going to be looking at we're going to walk through the derivation of the entropy of a substance and see how that changes with either temperature and volume or temperature and pressure. So we're going to start off with Boltzmann's equation, and we're going to start off the top. The total entropy inside of a control volume, S, is equal to the number of moles of the gas, if there's one gas here and it's an ideal gas, times R, the universal gas constant, times the logarithm of the number of microstates of the macro state in which the gas is in. Now, for a little bit more information on the microstates, you'll have to take take a course in statistical mechanics. What I want to point out here is that the number of microstates tells you something about the number of different ways that the gas could be located. Meaning there's a lot of empty space and there's gas molecules, so there's actually, it turns out there's a lot of different ways that the gas actually could be. And when you have a system like that where there's a lot of empty space, you have a lot of microstates. Whereas if you have the particles confined to small regions, you have a small number of microstates. And the actual definition is that the number of microstates is related to the volume. Scales like the volume is divided by the number of molecules, and is also divided by the de Broglie wavelength of the particles cubed. So that what's inside of that logarithm is unitless, right? Volume over particles divided by length cubed is dimensionless. So you can also take that equation divided by the number of moles, and you get a molar entropy is equal to R times log of the number of microstates. So when you actually put in the equation for the de Broglie wavelength, you find that for an ideal gas, the molar entropy looks like the specific heat at constant volume, i.e. 3/2 R right? So you get actually what happens is you get 3/2 coming off the logarithm times the constant times the temperature. And that 3/2 is equal to the specific heat of a ideal gas at constant volume. And then you also have the term plus R log of V over N, the number of moles. So if we want to look at how the internal molar entropy changes from state 2 to state 1, where the number of moles stays constant but the temperature and volume change, we see that the change in entropy from state 2 to state 1 is equal to the specific heat at constant volume times the logarithm of T2 over T1 plus the universal gas constant times the logarithm of V2 over V1. So this becomes the definition of how the entropy, molar entropy changes for an ideal gas. And using the ideal gas law, you can, if you rearrange the ideal gas law for V2 over V1 at constant N, you find that you can rewrite that equation as S2 minus S1 is equal to C sub P, right? Notice how it's C sub P, not C sub V now. So C sub P times logarithm of T2 minus T1, and now minus R times the logarithm of P2 over P1. So the way to think about this is that at higher temperatures, a gas is going to have more entropy than it does at low temperature. And it's going to have less entropy at higher pressures than it does at lower pressures. That's the way to think about it. Now in this course we're going to be using P and T because that's what is useful when we're talking about, let's say, the pressure and temperature of a flue gas or syngas or of compressed carbon dioxide. We're going to know its pressure and temperature. So that's why we're going to be using that equation with Cp and log of temperature minus R log of pressure. I do want to point out here that if you have a linearly varying specific heat, you have to make a correction to this. So this next equation below is what the equation looks like if you have a linearly varying specific heat, but still making the assumption of an ideal gas. And I want to point out in this last equation that if you have a mixture, you need to take the molar entropy difference of each of the species in the gas and multiply by the mole fraction of the gas and then sum over the entire. And just make sure that when you're doing the logarithm, the minus R log of P over P, that you're doing the partial pressure of the gas. Right? That should be the partial pressure at state 2 and the partial pressure at state 1. Okay, so I just discussed this topic of the linearly varying specific heat. So what I've graphed here is the specific heat at constant pressure divided by the universal gas constant as a function of temperature for the main gases of interest in this class. And I'm going to talk a little bit about it now, and then we're going to go into exactly the shape of it, and then I'll be showing you this graph again, and we'll talk a little bit more. So one thing to note here is that the difference for an ideal gas, the difference between C sub P and C sub V is 1R, meaning C sub P is equal to C sub V plus R. So as I said before, for if you have a monotonic gas, its C sub V should be 3/2 R. So its C sub P should be 5/2 R. And so of course on this graph we're not seeing anything, and none of these gases are anywhere near 5/2 R. You can see the hydrogen is around 7/2, is approaching 7/2 R, and oxygen, nitrogen, carbon monoxide are all near 7/2 R around room temperature. And then as you increase temperature, well, hydrogen really doesn't change, but oxygen, nitrogen, carbon monoxide start changing slightly, and you'd see that if you continued, you would actually reach about 9/2 R, which on this graph is 4.5. But we haven't gotten to high enough temperature. then you can see there's water vapor that's starting around a value of 4, which is 8/2 R. You got carbon dioxide, which actually is slightly below 4 at 200 K. Then we've got methane, which is right around 4 at 200 Kelvin, and then is increasing. So I just want to show you this, but we're going to come back and we're going to see why the specific heats are changing as a function of temperature. Okay, so to do so, we need to talk a little bit about the vibrational modes of diatomic and polyatomic gases. You can follow this link if you want some more. The website that links to shows you actually the different, shows you graphically the bending modes and other vibration modes of diatomic and polyatomic gases. So, first thing we're going to do is we're going to sum up the total number of degrees of freedom for a gas, a molecular gas that has n species in it. So if this is water vapor, n is equal to 3. So the total degrees of freedom is equal to 3n, meaning each of the 3 species hypothetically could move in the x, y, and z directions independently. So there's a total of 3n degrees of freedom. Now when you put them together into a molecule, what we say is that that molecule has 3 translational degrees of freedom, meaning the entire molecule could move up to the side or front and back, basically x, y, and z. And then that molecule has a certain number of rotational degrees of freedom. If it's a linear molecule, let's say nitrogen, oxygen, carbon dioxide, we call it linear, and then it has 2 rotational degrees of freedom. It doesn't have 3 because about that axis there's no moment of inertia. So like if we have nitrogen here, along the axis that goes between the nitrogen molecules, there's no moment of inertia. The 2 rotations are in which the nitrogens actually are moving. Okay, if it's a nonlinear molecule such as water vapor, then there are 3 rotational degrees of freedom. So if you want to calculate the number of vibrational modes for a gas, you calculate 3n minus the number of translational degrees minus the number of rotational degrees. So for a linear molecule, that's going to be 3n minus 5 vibrational modes. For nonlinear molecules, it's 3n minus 6. And now we can start counting up the total number, the total specific heat of a gas. So for each degree of translational degree of freedom, a gas has 1/2 R contributing to the C sub V. So if this is a monotonic gas like argon or neon, its C sub V should be 3/2 R because there are 3 degrees of freedom, and each degree of translational freedom adds 1/2 R. Now it gets a little bit more complicated for some of the other molecules. For the rotational degrees of freedom, it's going to contribute 1/2 R, provided that you are well above the characteristic temperature of rotation. And that characteristic temperature depends on the type of molecule. Heavier molecules, that characteristic temperature is lower than light molecules such as hydrogen. But provided you're above that characteristic temperature, then each rotational degree of freedom contributes 1/2 R to the specific heat at constant volume. So if we are nitrogen and we are above the rotational degrees of freedom, and if we are below the vibrational degrees of freedom characteristic temperature, we should find that the specific heat at constant volume is 5/2 R, meaning there's 3 translational degrees and 2 rotational degrees of freedom. Okay. Now, each vibrational mode can contribute 1 R. Not in the other cases, there's 1/2. The vibrational modes can contribute 1 R. So if you're oxygen and you are above the characteristic temperature of vibration, then you can contribute, you'll have 3 plus 2 plus another 2, so you have 7/2 R as the specific heat at constant volume. But if you were at, if you're below the characteristic temperature of vibrations, then you're only going to be at 5/2 R. Okay. So this is the graphical way of what I was just talking about. This is for a diatomic gas when you are either below the temperature of rotation, in between the temperature of rotation and the temperature of vibration, or above the temperature of characteristic temperature of vibration. And as we saw, it's 3/2 CV is equal to 3/2 R. And as you start increasing temperature, you start activating the rotational modes, and then you're at 5/2 R. And then as you continue to increase temperature, you're going to be activating the vibrational modes, and then you saturate out at 7/2 R. The equation that plots the C sub V due to that vibrational mode is extremely complicated. And if you had to integrate this in this class, you'd probably take an entire week just trying to, or you could take an entire day to do some of these calculations. And what I want to point out here is that it's a really complicated function, but when you are close to the point in time in which you are just coming out of the flat line in between the temperature of rotation and temperature of vibrations, it looks fairly, you can put in a linear approximation to it. So let's go back to this graph here and see what's happening here. So let's first look at the hydrogen. So hydrogen, we can see, hasn't yet hit 3/2. Hasn't hit 3.5 on the C sub P. And that's because it's at 200 K, it still is not completely rotationally active. It's not until you get to about 300 Kelvin that it's completely rotationally active. And then it stays fairly constant along between 300 Kelvin and 1000 Kelvin. This is because the vibrational mode for hydrogen is not active yet. Whereas for nitrogen, oxygen, and carbon monoxide, that vibrational mode is starting to become active. And it's the oxygen one that is starting to become more active than the others, because oxygen is slightly, ever so slightly heavier, and but there's also differences in the bond lengths, the weights, but it's the oxygen one that is being active a little bit faster than nitrogen and carbon monoxide. Okay, so then we have water vapor. We saw that C sub P, once you are above the characteristic temperature of rotations but below the characteristic temperature for vibrations, should be 4 R. And that's what we're finding here. And then you see its rotational modes are starting to become active, and actually it's a very good linear fit between 300 Kelvin and 1000 Kelvin. Carbon dioxide, as a linear triatomic molecule, should have had a value of 3.5 R for its specific heat at constant pressure. But you can see it's already at 200 Kelvin, it's already above that. And the reason is that it has a symmetric vibrational mode that is already active starting to become active at 200 Kelvin. And you can see the character shape of this curve. It's not purely linear as let's say for the water or oxygen and the other ones. You can see here that some of these bonds are already starting to become saturated. And but carbon dioxide has multiple bonds. It's got symmetrics, it's got an asymmetric, and it's got like these bending vibrational kind of modes. And so a lot of these modes are starting to become active, which is why there's a a fairly large change in C sub p over this temperature range. And then now, when you get to methane, you now have a molecule that has, there are five molecules, so there's 15 different possible degrees of freedom. And then if you subtract off the 3 translational and the 3 rotational, what you're left with is going to be 9 degrees of vibrational. So you have the potential with methane to have a very, very, very large C sub p once you get to the mode, once you get to the temperature in which all of those modes are being activated. But when you combine all those, it just kind of lucks out that between 300 Kelvin and 1,000 Kelvin, like the range that would be of interest, mostly for methane, we don't need to go much above, unless you're reforming methane, you don't really need to go above these temperatures. And what we find is that it's a linear fit through this range. Okay, so now we're going to move on to the next part of this lecture, which is where we start talking about ideal gas approximations and real gas modeling, when you start taking away some of the assumptions in the ideal gas model. So let's first go through and look at what all those assumptions are. So the first assumption is that all collisions are elastic. That means the molecules essentially do not see each other. There's no attractive or repulsive force except just as they collide, and then they perfectly bounce off of each other and then go back to completely not knowing that they're there. So there's no attractive or repulsive force until they, except at the origin where they collide into each other. And there's also the assumption that the particles themselves have negligible volume, meaning that they take up a negligible amount of space compared to the characteristic distance between molecules. So the assumption here is that the distance between molecules on average is much, much greater than the size of the molecules themselves. Another assumption is that the velocity is randomly distributed, that we don't just have flow all in one direction, that the velocity is distributed randomly. And when you have that, you can use the ideal gas law, which is that the pressure times the volume is equal to the number of moles times the universal gas constant times the temperature. Okay. So as we know, in the real world, not everything is a gas. And so what I'm showing here is just an example of for carbon dioxide, and I'm using carbon dioxide because when you sequester it, you don't sequester it as a gas or as a liquid or as a solid. You sequester it as a supercritical fluid. So I just want to talk a little bit about that. So on the right here we have a pressure temperature diagram for carbon dioxide, and you can see a region in which it's a gaseous. You can see a region where it's solid, and actually at there's going to be gas, solid, liquid, and supercritical fluid. One thing I want to note here is that there's only one triple point, and then there's lines that are going to be connecting the various regions. So there's something called the Gibbs phase rule, which tells you the number of degrees of freedom in describing that phase. So degrees of freedom are things such as pressure, temperature, and it could be composition if you have multiple components. C is the number of components. So in this case, if it's carbon dioxide, then there's only one component. But you could have these type of graphs if you had, let's say, water and sodium hydroxide in solution. And then P in the equation is the number of phases in thermodynamic equilibrium. So let's see how this equation works out. Let's start with carbon dioxide, in which we have one component, and we want to know how many degrees of freedom are there such that all three phases, solid, liquid, and gas, are in equilibrium. So we go and we put P is equal to 3, C is equal to 1, and what you find, of course, 1 minus 3 plus 2 is 0, right? So there are no degrees of freedom. So once you specify that, that's the triple point. There is no degrees of freedom about the triple point. So let's ask the next question. What's the, let's have the gas and liquid phases in thermodynamic equilibrium. So in that case, P is equal to 2, C is still 1, so now the degrees of freedom is 1, right? So for any pressure, well, any pressure between the critical point and between the triple point and the critical point, once I specify a pressure, that fixes the temperature. So basically we went from there's going to be a line that links the triple point and the critical point. So there's 1 degree of freedom. You can specify a pressure, but then that fixes the temperature. So the next one we'll look at is if we just have one phase in thermodynamic, if we just have the gas with no liquid in it. So now P is equal to 1 and C is 1. What we find is there's 2 degrees of freedom. So in the gas phase, you have 2 degrees of freedom. You can specify the pressure and temperature independently of each other. And the same is true in the supercritical fluid or in the liquid state. In any single one of those, you can have 2 degrees of freedom. Okay, so that's the Gibbs phase rule. What I want to point out, the other thing I want to point out is, so when you're at low pressure and high temperature, the ideal gas equation is going to be valid. But as you start getting towards this critical point, and either approaching supercritical fluids or liquids, that's when the ideal gas law is going to start breaking down. And you're going to have to make some other type of model or approximation. So now we're going to look at how at a constant temperature, if you change the pressure, you'll see, as you increase the pressure, you see deviation from the ideal gas law. So what I'm graphing here is, and this is from the website below, the ideal gas law as PV over RT, basically the compressibility of the gas, and showing how that deviates from a value of 1, which would be the ideal gas law. And what we see here, let's start off with hydrogen. In the case of hydrogen, PV over RT is always slightly greater than 1, and as you increase the pressure, it gets more and more noticeable. So what it's saying is, for any given pressure, the volume is actually greater than what you would have expected from the ideal gas law. And so for the case of hydrogen, that's the case that it actually has a small amount, the hydrogen molecule itself has some size, so as you go to higher and higher pressure, one of the assumptions from the ideal gas law gets violated, and that's the assumption that the molecule has no space. Okay, so hydrogen was the easiest one here. And that's because there's virtually no intermolecular forces between a hydrogen. So now let's look at another extreme, like carbon dioxide. Carbon dioxide, you can see PV over RT drops significantly and then starts coming back up again. So it's that drop down that I want to explain. So the volume that it takes up is less, and less by if you're at that little bend in it's less by over a factor of 2. The volume taken up by the gas than what you would expect for an ideal gas. So what it's saying here is there's actually some intermolecular attraction that is keeping the molecules closer together than what you would have expected if it was an ideal gas, and no attraction. So what's happening here is that you increase the pressure and PV over RT gets as low as about 0.4, and then as you increase pressure again, what's happening is you're now getting it to the point where they're so close together that the repulsion is starting to take over, and they're pushing each other away from each other, and you can actually get to the point where, once again, the ideal gas law is technically valid, right? It's a very, very small range out near about 500 atmospheres. And so that's also the same reason that the methane and nitrogen curves have the shape that they do. And what it's saying here is that the CO2 has stronger attraction than methane, but methane has more attraction than nitrogen. And of course, hydrogen has virtually no attraction to other hydrogens, which is why you don't even see the dip down in the curve. It just stays above 1 the whole time. So let's take a look at what I mean by the attraction and repulsion. So what I'm graphing here is the distance between two like molecules. And so this axis is if the two molecules were exactly, the y-axis here is that basically the distance is equal to 0, and the molecules are on top of each other. And there's a repulsive force, which is this lightly dashed line, and the repulsive force is 0 until you get really, 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 really close, in which you have the nuclei repulsing each of the two molecules, providing a repulsive force. But you also have attractive forces. So for two molecules coming together, instantaneously a molecule could have a dipole moment show up, and instantaneously the other molecule could have a dipole, and those dipoles could be attracted to each other. So you don't need a standing dipole to have attractive forces. So like in nitrogen, you could instantaneously have a dipole just through quantum fluctuations, and you could have quantum fluctuations in another nitrogen molecule, and they could be momentarily attracted to each other. And because of that, even species that don't have net charge, like nitrogen or oxygen, can actually be attracted to each other, like nitrogen to nitrogen and or nitrogen to oxygen. And because of that, the shape you get is this kind of well, and with the location of the minimum in the well is defined here as b to the 1/3. I'll explain b in just a second. And the depth of the well is defined as a. So a molecule is going to have a certain depth of attraction and a distance at which that minimum occurs. The value of A is related to how strong the attraction is, and B is ultimately related to the size of the molecule. B is going to be the volume. B to the 1/3 is something about the linear dimension of the molecule. So these are the assumptions that go into the van der Waals approximation. And so there's these two constants, A and B, and from A and B you can calculate what the critical temperature and critical pressure should be. And so as we saw in that graph before, the critical temperature and pressure is that point in which liquid, gas, and supercritical fluid are all starting to come together. And so that supercritical temperature looks like 8 times A over 27 times B times the universal gas constant. So a molecule that has a very large attractive force, A, is going to have a high critical temperature. But the larger the molecule is for a given A, that supercritical temperature is going to start dropping again. So it's not just A, it's A divided by B that's important. For supercritical pressure, it's A over B squared that is important. And so from those, if you know the critical temperature and pressure, you can actually calculate what A and B are for a van der Waals gas. So here I'm showing you for the gases of interest in this class, experimentally what their critical pressures and temperatures are, and then what that corresponds to as far as the van der Waals attraction. So it's the depth of the well, A, here A prime, and then the van der Waals size, which is B prime. So let's go through the critical pressures. What you should notice here is that water vapor has a very, very high critical pressure compared to most gases. And let's say hydrogen has a very, very small critical pressure. And the same goes with critical temperature. Water vapor has the highest critical temperature, followed by carbon dioxide, and then methane, and then we have nitrogen, oxygen, carbon monoxide, and then followed the smallest one here being hydrogen. So when you're at a very high critical temperature, when you're at a high temperature compared to the critical temperature, that's where it's safe to make ideal gas approximations. And when you're also it's safe to make ideal gas approximations when you're at high temperatures and low pressures. So that's high temperature compared to the critical temperature and a low pressure compared to the critical pressure. What I want to point out here is using the equation from the last slide, you can calculate the A prime and B prime for these gases, and you can see the molecules with the largest A primes are water vapor and carbon dioxide. And of course, the hydrogen has that smallest attraction between each other. So, as we mentioned before, so the reasons why the ideal gas approximation will break down is, one, real molecules have a certain size, and then real molecules actually have intermolecular attraction or repulsion. They're not just perfect billiard balls. Most of the gases in this class can be treated as ideal gas, but there's definitely some exceptions to that, and that's going to be water vapor. And that's going to be water vapor. Under most cases, you should not be using the ideal gas law for water vapor. There are very few times in which you should be using the ideal gas law for water vapor. And that's why in this course we're going to be using XSteam, a macro, a free macro that we can find on the web. For other gases such as compressed carbon dioxide or natural gas, we're going to be using a first order approximation, a first order correction to the ideal gas law. And so let me talk to you a little bit about what I mean by the first order correction. So Z, which is the compressibility factor, which is PV over RT, which can also be written as P over rho RT, where rho is the number of moles per volume. You can write that as, you can just expand it out as either a function of pressure or as a function of the density, molar density. When you do it as a function of pressure, Z can be written as 1 plus B2P times P plus B3P times P squared plus, and then order P cubed plus, higher order terms there on out. You could do the same thing, and it's called the viral expansion with respect to density, and then it's going to be a 1 plus B2V times rho plus B2V times rho squared plus higher order terms. So the equation of, say, for a van der Waals fluid, which is shown over here, you can see that there's a correction for, it goes to the ideal gas law when A and B are equal to 0. When you work out for the van der Waals fluid, what you find is that for the first order corrections, B2V is equal to RT times B2P is equal to B minus A over RT. So this basically gives us the way of making a first order correction to the ideal gas law. So let me show you what this means. Okay. So on the right here, I've got a graph of what's called the fugacity coefficient, F over P. So let me talk to you first about what F over P is. So if we look at the bottom equation, the log of F over P is equal to Z minus 1. So Z minus 1 is essentially how much a gas deviates from the ideal gas law. So when we say the logarithm of the fugacity coefficient is telling you how much a gas deviates from the ideal gas law. So if we look over here, the fugacity coefficient would be a fugacity coefficient of 1 means you are at the ideal gas law, right? Because log of 1 is equal to 0, which means z is equal to 1. So when you're at really high reduced temperatures, and a reduced temperature is the temperature divided by the critical temperature in this graph, and then this graph here is showing you the fugacity coefficient as a function of the reduced pressure, P over P critical, and each line on the graph corresponds to a different reduced temperature. If you see here, very high reduced temperatures, and for low values of PR, you're at a fugacity coefficient of 1, meaning you can treat it as an ideal gas. So when you're above a critical temperature of 2 and the reduced pressure less than 2, then ideal gas law is perfectly valid. Now as you start dropping the reduced temperature to about getting close to 1, so between 2 and 1, and what you find is you're only you can linearly approximate the change in the fugacity coefficient with respect to pressure. And in this region is what you're starting to get close to the supercritical. You're getting close to supercritical. And here we're going to be using a first order approximation. And so that's what we'll talk about, the van der Waals approximation, or the van der Waals approximation is a first order kind of correction. When you get to temperatures much lower, and the van der Waals is going to break down when you get to reduced temperatures below the critical temperature. So what you can see here is that you cannot make linear corrections because it greatly depends on what your reduced pressure is. And you can quickly deviate from 1 when you're at below the critical temperature. So the first order corrections are only valid up in this kind of the region close to 1. And when you're outside of that, it's best to use something like a steam table, where you just kind of type in the temperature and pressure, or you put in the temperature and pressure, and then you kind of look up what the values are of, let's say, enthalpy, entropy, or anything like that. So that's why in this class we're going to be, because steam had such a high value of critical temperature, that's the reason why we're going to be using basically steam tables, Excel-based steam tables. But for other gases like carbon dioxide and methane, we're going to be able to get away with a first order kind of van der Waals approximation. I want to point out that so in this class we're going to be interested in knowing like what is the enthalpy and what is the entropy. I'm putting up these graphs just so you can see how much they deviate from their values if they were ideal gas law, if they were an ideal gas. But as I said before, for steam we're going to be using macros, so you don't actually have to look this up by hand. And once again, I just want to point out that you can see there's regions where you could use a linear approximation, but as soon as you get to less than the critical temperature, that's where you get into the region where you have part vapor, part liquid, and then if you continue to go, let's say, higher pressure at these lower reduced temperatures, you get into the purely liquid state. So let me show you what these first order corrections look like. For the enthalpy, the generic equation is that the change in the enthalpy as a function of pressure at constant temperature looks like the volume minus the temperature times the change in volume with respect to temperature at constant pressure. For the first order real gas approximation, that looks like B2V minus the temperature times the derivative of B2V with respect to temperature. So in a couple equations above, I say that B2V looked like B minus A over T, RT. So what this does is it gives you some terms. So when you're calculating the change in the enthalpy between state 2 and state 1, you're going to have the correction due to temperature, which are these first two terms, the first term being the T2 minus T1 term, and we have a T2 squared minus T1 squared. And then we have this correction due to pressure. So as I said before, for an ideal gas, the enthalpy is not a function of pressure. But when you do the first order correction, you get a term that has P2 minus P1 in it. Now for the entropy, the change in entropy with respect to pressure at a constant temperature looks approximately like minus the derivative of B2V over dt. And so in that case, we need to add. We have terms for the temperature, and then we have that minus r times the logarithm of P2 over P1. But now we need to make another correction, and this is the correction that accounts for the real gas behavior, the first order real gas behavior. And the other thing I want to point out is, as you can probably see in the equation, that for the first order real gas behavior for the Gibbs free energy just looks like B2V. And that's because there's a, you can see if you multiply ds by dp, a constant temperature, by temperature, and then subtract that off from the dh dp term, you can see that's why those two terms are canceling, and you're left just with B2V. Okay, so what I have here are, for the gases of interest in this class, the values of the specific heat at 300 Kelvin, the slope, so the linear approximation, so that's the slope, the change in C sub P with respect to temperature. We have the partial pressure in the atmosphere, which I'll be talking about later when we get to the concept of exergy. And then I also have two columns here for the standard enthalpy of formation. So that's the enthalpy at room temperature and pressure. And then I also have the standard entropy of formation, delta S naught. Those two columns, you need, of course, to calculate the entropy or the enthalpy of a gas, you need or of a liquid, you need a starting point to be able to calculate from. So we're going to be using these as our starting points. And then I've also given you the A prime and B primes for these gases so that you can calculate first order corrections. So what we'll find here is, with the information we have here, we can model almost all gases of interest at power plants except for water. And I've put up here both water as a gas and liquid, just so you have a reference, but realize that for water we're going to be using basically macros that are steam table macros. But with the steam table macros and the information you have here, you can do almost any calculation that you need to at any calculation you need at a natural gas combined cycle power plant. To do for a coal power plant, you're going to need some information about coal itself. But once you have the information about the coal, you have virtually all the information you need to design a coal power plant.